All right, let's have an introduction to shear and bending moment diagrams. So we just learned how to solve for the internal forces at a point. And that's great, but I told you just to the right of D. Well, what about just to the left of D? What about halfway between, C and D? I mean, there's infinitely many points along that beam. How do we know that D is the important one? So that's where shear and bending moment diagrams come in. Since the internal shear and moment often vary greatly along a beam, plotting the internal shear and moment along the length of the beam can be extremely useful to help determining where there are maximum or minimum values. To do this, we follow a very similar procedure to what we just did, but instead we make our cut for our free body diagram at a variable point that is x from an end. And I say the left end, it's usually the left end, but you're cutting it at a distance or a length of x as opposed to a definite location. So then when you determine your equations, you'll see that they're all going to start being in terms of x a lot of times. They're going to be functions and not just values. And there's a couple of different ways that people do shear and bending moment diagrams, and there are faster ways than this, but I'm teaching you how to generate the equations because this is the much more fundamentally, like if you understand this, all the other methods will start making a lot of sense. So don't get too distraught when you see like you have to develop all these equations and it's real slow and laborious, because there are much faster ways. You'll learn those in future courses, like graphical methods of recognizing the calculus involved and just finding the areas of rectangles and triangles and things. And it's really fast and easy, but this is a great introduction into understanding what really is going on. And a lot of times you do need the moment and shear equations as functions for other courses as well. So this is certainly going to be something that you will do again. So the procedure for this: determine all the support reactions on the beam, resolve the forces into components acting perpendicular and parallel to the beam's axis. So I go ahead and solve for all the reactions when I do shear and bending moment diagrams. And then I determine the shear moment function. So to do that, I have to say, well, how many free body diagrams am I going to need? If I have a point load right here, that's a discontinuity, right? So I'm going to have two free bodies. I'm going to have a free body that's cut over here to the left and a free body diagram that's cut to the right of that point load. And I can keep the left-hand side or just keep the right-hand side. I usually work from left to right when I do shear moment diagrams for many, many reasons. Sometimes it might be a little bit longer equation, but it just makes a lot more logical sense as you're trudging your way across. So you can see here, I now have like our X1 region. So this X1 would be for anything between A and C, and then X2 is the equations I would get for the cut that's anywhere between C and B. So this is what those free bodies would look like. You can see here's the first one, which is valid for this X1. The X1 and X2, those are just, like it's really all X, but it's just subscripts to help you remember, are you in the first region or the second region for the applicable domain of X and all that jazz. We'll see it in an example here. So we cut our free body and we just solve, just like we did before, but now we're going to have oftentimes that X showing up in a lot of things, right? I mean, think about it. Even the distributed load now, the resultant of it is going to be a function of X, because the resultant of a distributed load is base times height, right? So maybe that's 100 pounds per foot, but this is X long. It's not 10 feet anymore. It's not 2 feet, it's X. So we're going to have a lot of things that are functions of X. Think about the moment. The distances are all also going to be dependent on X. We are going to determine our shear moment functions by, for shear, summing forces in the Y, which is the axis perpendicular to a beam's axis. So we're just doing a beam. And then for moment, we're going to sum about the cut, like I said, some moments about that cut in, so that we don't have functions times distances. We have, reaction values times distances. It makes our math a lot easier. And then we'll draw our shear moment diagrams. And if your answer is a function, then you would plot your start and end values. You plug in your start and end X values into your function, find the start and end values of your shear. Look at your function. Is it a line? Is it positively sloped? Is it a quadratic? Is it a concave up or concave down? You can look at the math like you've been learning since high school and recognize how to draw these functions. So for instance, this beam right here would end up having a shear function look like that and a moment function that look like that.